Okay, so welcome back to part two. Let's talk about contraction mappings. So f from a subset of a normed linear space E back to itself again. And I really think that the mapping f is supposed to go from A to A. He doesn't seem, his language is not clear in the book, but well, we'll see in an application where it matters. Um, it's supposed to go back into A again, at least in the application I have in mind. So I really think that maybe this should be A. But okay, anyway. Um, I'll have to look into it more before I meet with you guys again. But anyway, it's a contraction mapping or a contraction if there's a positive alpha less than 1 such that like the norm of the difference of the values at x and y is less than or equal to alpha times the length of the xy displacement vector there, right? And that has to hold for all pairs x and y and a. And one of the things you can prove, of course, is that contraction maps are continuous. So to see that it's continuous, here's a simple argument. And here I'm using the epsilon delta definition of continuity because it's just what appeals to me at the moment. But you know, maybe there's a lazier way to do it given everything else we've done. I just, you know, a little bit sleepy at the moment, so I'm going to go with that. Sorry, guys. But anyway, epsilon greater than 0 if we let delta equal to epsilon over alpha. If x naught's a point in A and we're within distance delta of x naught, then the difference of f of x and f of x naught with the norm is less than or equal to alpha times the norm of that, because f is a contraction, and then that is by our choice of delta less than epsilon over alpha times alpha, which is epsilon. Therefore f is continuous at x naught. X naught being arbitrary, we have shown that the mapping is continuous. Okay, so contractions are continuous. That is true. Now, here's an example, and so he really only has one example in section 1.5. I'm going to add some material from another book for this part of the lecture, which is part of the reason I didn't want to Zoom today, because I have like a bunch of really small print that you'd need to kind of look at, and if we tried to do it over Zoom, it just wouldn't work. But I mean, this example's fine. I could have done this on a board, but consider x cubed minus x minus 1 equal to 0. And so I know, like, you're like, well, what does that have to do with the contraction? Well, fine, just stick with us here, okay? So you might want to solve this equation. And, you know, he says it has 3 roots. He doesn't prove it. What we do have proof of down here is that you know, you can recast this as a fixed point problem. Like, a fixed point problem means that t of x equals to x. That makes x a fixed point of t, all right? So you can recast this equation as a fixed point problem for t is equal to 1 plus x to the 1/3 power, or you could use x cubed minus 1, or you could even use this. Any of these are choices that you could use for operators for which, you know, fixed point, and I say operators, but I really here just mean function. These would be functions whose, if they did have a fixed point, it would be corresponding to a solution of that equation. Now, it turns out that he doesn't really do anything with this one or that one, so the book just focuses on this guy right here, which is fine. And just to point out, if we look at g of x, just the, you know, I define that to be the equation, the formula for the equation, rather. And if you look at g of 1, you get minus 1. Look at g of 2, you get 5. So, okay, so by the intermediate value theorem, there has to exist a c between 1 and 2. Since, of course, g is continuous, there has to be an intermediate value that goes to 0. So we know there's a root to find. Let's just say that. All right. All right, so what we're going to do for this part of the lecture is we're going to show that, in fact, this map here is a contraction on 1, 2, just to give us an example of a contraction, okay? All right, so let's see here, the derivative of t is this, which you can rewrite as that. And if you look at that, that's less than or equal to 1 over, so the biggest this can be on 1 to 2 is when you put in 1 for x, right? Anything else would make the denominator larger and hence the fraction smaller. So this is the maximum value on 1, 2 for the derivative. And in fact, the slope of the function is always less than this elsewhere, all right? But that being said, we can apply the mean value theorem for any pair x, y in 1, comma 2, and by the mean value theorem we have that t of x minus t of y over x minus y is equal to the, well, t prime of c for some c in 1, 2. Okay, fine. To be more honest, it's for c between x and y, right? But that's kind of immaterial. The point is that there is some c in here which is bounded, which is the average rate of change is equal to the instantaneous rate of change. Of course, that's the mean value theorem. And so taking absolute values of this equation, we get the absolute value of tx minus ty is, of course, by definition that. And that is less than or equal to the bound I found on the derivative times the absolute value of x minus y. So, okay, so hey, that means that, in fact, this is a contraction mapping. T of x is a contraction mapping on 1, 2 with contraction constant third root of 2 divided by 6, which is in fact less than 1. So that's, that's pretty neat. Now you might say, who cares? Well, okay, fine. Maybe let me just skip ahead and show you why we care. The reason we care is given in part at the end of the section, all right? So like, it turns out that the fixed point of that map can be obtained in an iterative fashion. All right, so like here it is at the end of the section. He kind of, like, this example in and of itself is not interesting. It's interesting because of what's said later in the section, right? So like later in the section, page 34 of the textbook at the end of section 1.5, he's like, okay, so we have proved it's a contraction mapping, and its fixed point is the solution of the equation, right? So what he does is he puts an initial guess of 1. Of course, 1 doesn't work, right? But when you feed 1 into the mapping T, you get the cube root of 2, which is about 1.2599. And then that isn't, quite right, but that's fine. You take that and you make that x1 and you plug that into T again, and you get this. And then you take that and you plug it into T again, and you get that. And you take that and you plug it into T again, and you get that. And you take that and you plug it into T again, and you get that. And you take that and you plug it into T again, and you get that. And if you start looking at these numbers, you'll start noticing that we're settling on 1.3, 1.3, 1.3, 1.3, right? And then as you keep going here, look at this. Then all of a sudden 2 is stabilizing, right? And then the 2 is changing, but then it settles on a 4, right? And then by the 7th, going to the 6th to the 7th iterate, up to 4 decimals, we're not even changing, right? So this is actually an approximation of the root of the equation that we were just looking at, x cubed. I've already forgot it. X cubed minus, my bad, x cubed minus x minus 1. This has an approximate solution of 1.3247. And how did you find that? You found it by finding a contraction map that corresponds to the equation. You make an initial guess, and then you just follow this iterative sequence of feeding the point, feeding your initial guess to the contraction map, and then operating repeatedly. And it turns out that sequence has to converge to the fixed point of the map, and because we've constructed the map so that the fixed point corresponds to the solution to the equation, we've solved the equation by iterating. That's weird. That's really weird. And it's also beautiful. And it's also the heart of pretty much every existence theorem that I know of. So let's get to it. All right. So the theorem that is behind that is Banach's fixed point theorem, which is, I would argue, probably the most important theorem I've showed you so far this semester. And on top of that, this is a theorem, most, I think, beautiful from a perspective of an instructor, that I don't feel unreasonable putting on a test. Like, I think you guys should be able to prove this theorem. So, when you find something that is both simple and amazingly applicable, That's a rare gem, and that's what we have here. So let F be a closed subset of a Banach space E, and F a contraction mapping of F into F. See, now it's a contraction mapping of F into F. Okay, so we're definitely we're making it go from A to A in practice, aren't we? I feel like that should be part of the definition of contraction, but maybe people have other opinions, whatever. Then there exists a unique Z in F such that it's a fixed point of F. All right. Here's the proof. Suppose you've got a contraction map, all right, and pick a point, any point in your closed space F, and then define a sequence by iterating on F, right? So your nth term in the sequence is obtained by taking the n minus 1th one and operating by F, all right? And you do that for every natural number. Well, what does that do? Well, check it out. So x to the n plus 1 minus f minus xn is by definition f of xn minus f of xn minus 1. But hey, f is a contraction map. Therefore, this is less than or equal to alpha times the difference of xn and xn minus 1. But having done this trick once, we can do it again. Replace xn with its f of xn minus 1 and x sub n minus 1 with f of xn minus 2. And again, f is a contraction map, so we apply it again, and we get that. So once you do this twice, you realize you can keep doing it, continuing in this fashion. And of course, you could supply a formal induction there if you wanted to get all rigorous and stuff on me. But let's just not do that and stay on point, because everybody can do the induction, right? Okay, fine. And anyway, so x sub n plus 1 minus x sub n apparently is alpha to the n times the norm of x1 minus x0. So that's, quite beautiful. And, I would just also point out, like, from a pragmatic perspective, if you think about what this means for the sequence, it means that well, it seems like you can use this to somehow find like an estimate on how far you are, perhaps how far you are from the fixed point. But I'm speculating at the moment. That's not part of this theorem. Let's just go on. Anyway, so for any m and n, where m is less than n for convenience, look at this. We can take xn minus xm. We're going to prove right now. We're going to prove that, in fact, this is a Cauchy sequence. Let's see how that happens. It's going to be just a bit here, but it's a pretty straightforward calculation, actually. So what we do is we just add 0, right? And then use the triangle. Well, no, we're not even adding. Okay, fine, we're adding 0 between the xn and xm, just adding all the changes from getting one to the other. And then apply the triangle inequality a bunch of times to get like that. And then apply our I don't know, I should give this a name or something. We'll apply star on each one of those terms, yeah. We'll call this thing star. It is the star of the show after all. Oh, I'm sorry, that's horrible. My bad. Anyway, so applying that, we get ourselves a, alpha to the n minus 1, alpha to the n minus 2, alpha to the m added together, and there's a common x1 minus x0 norm everywhere. And then, at the heart of everything interesting, the geometric series appears. So basically, if you just factor alpha to the m out, it would leave you a sum of powers of alpha, right? And, well, like 1 plus alpha squared plus da-da-da, alpha to whatever that is, n minus 1 minus m. And then just keep going. Just add the whole series, and you're just adding positive terms. And no harm, no foul, because it converges because alpha is less than 1 and it's positive. So we can do that. And it's clearly a strict inequality there. And more than that, we also know it converges to 1 over 1 minus alpha. So we get alpha to the m over 1 minus alpha times the norm of x1 minus x0. And, Well, since alpha is less than 1, this goes to 0 as m goes to infinity. Voila, it's Cauchy. So we have a Cauchy series, and Cauchy sequence rather. But what's our context? Well, our context is closed space, right? We're in a closed subset of a complete space. We've got a Cauchy sequence by construction then. By definition, since we're in a complete space, it converges to a point in the space, which we call Z. And our claim is simply that that is the fixed point we're looking for. So to prove that, look at this. The norm of f of z minus z is adding 0 here by adding and subtracting xn. We get this. But then again, by the definition of the iteration, that is f of xn minus 1. And again, f is a contraction, so we can pull that back to alpha times z minus x n sub n minus 1. But hey, both this and that go to 0, right? It doesn't matter if you've got an n or an n minus 1. Either way, the fact that xn goes to z as n goes to infinity means that this and that separately go to 0. Consequently, it all goes to 0, which goes to show you that that norm must be 0. And if that norm is 0, that means f of z is equal to z. Right? And if f of z is equal to z, well, that's it. Well, it's almost it. We still need to see uniqueness, right? So suppose f of w equals to w for some w and f, then notice that the norm of z minus w is the norm of f of z minus f of w, which is by the contraction property less than or equal to alpha times z minus w for some alpha, which is between 0 and 1. The only way you can have this is if the norm of z minus w is equal to 0, right? Think about it. If alpha is a half, can you have the norm of z minus w is less than or equal to a half the norm of z minus w? No, sir, you can't do that unless the norm of z minus w is 0. And if the norm of z minus w is 0, well, z is equal to w, consequently unique. That's it. That is the proof of the Banach fixed point theorem. It's simple, and it's not just that. So many theorems we come across that are awash with contradictions and so forth, like proof by contradiction. That's not here at all. It's all constructive, and it actually is laying the groundwork. It's showing you the path for how to actually construct the solution iteratively. Now, okay, in practice, maybe you don't want to do that for an actual problem, right? But, I don't know, maybe you're a numerical methods guy and you do, you know? So, this right here, switching gears a little bit, is a couple pages of notes I wrote up on Newton's method and the contraction mapping, because I think that's the first application you ought to see. And this is taken from Advanced Calculus of Several Variables by C.H. Edwards, Jr. In particular, I'm looking, around page 162-ish. So he's got a whole section on Newton's method and contraction mappings. And this book is where I first, I think, really appreciated how important and interesting the contraction mapping idea is. So, not a perfect book, but I've gotten a lot out of it over the years. Okay, so let's go through this, and I will share this with you guys, of course. So you don't have to write all this down if you don't want to. But and sorry, my handwriting is a little sloppy in here. I wrote this a while ago. So just to start with, the basic starting point is Newton's method. All right, so if you want to solve f of x equal to 0 by guessing x naught, then first of all, you plug it in and see if it works, right? And if it's not equal to 0, then what do? Well, you replace the function with its linearization. What's the linearization of the function? Well, it's f of x naught plus f prime of x naught times x minus x naught, right? And so if we solve this, set that equal to 0 and solve, call that solution x1, solve that for x1, you get x1 is equal to x naught minus the ratio of f of x naught and f prime of x naught. Now, if f of x1 is equal to 0, we're done. Otherwise, we let x2 be the solution to the linearization at x1. And you do the same algebra, and out pops x2 equals to x1 minus f of x1 over f prime of x1. Well, this seems a lot like what we were just doing with contraction mappings, doesn't it? Um, I mean, okay, that's kind of like historically opposite of the situation, right? Newton's method came first, and it was people thinking probably about Newton's method and other related methods that eventually led Banach and um, so forth to actually find that theorem in the way they did. But anyway, so this suggests then that like you should iteratively define xn plus 1 by xn minus f of xn over f prime of xn. Now, this is what Edwards calls naive. It's naive Newton's method. It's cumbersome, and generally speaking, the limit doesn't even exist. I mean, you know, the standard example. That was just I just had it out here for a second. Let me try not to blather on too long here for you guys, but you know, this can happen for Newton's method, right? Like you start here, and then you get thrown over here, and then it's got the same slope. The zero of the new line gets you back where you started, and then you just keep iterating, never getting to the middle where the zero actually is. That could in principle happen to you. So like the solution is to go to something more like this, where instead of just you find like the maximum slope and kind of just keep always going down by that maximum slope and that'll stop you from doing that loop-de-loop like I just showed you. Okay, so so here's the claim. The claim is that if the difference of sign, if f of a and f of b have a different sign, and the derivative is bounded by m, like the slope is no more than m in magnitude, right, for all x in this closed interval, then the sequence defined inductively as such, so you do xn plus 1 is xn minus f of xn over m, all right, converges to x star and f of x star is equal to 0, all right. Now, to prove this, he first proves the contraction mapping theorem. Now, the contraction mapping theorem here is stated for a function on a closed interval to a closed interval, right? That would be a very special case of our Banach space with a closed subspace, right? And here the norm is the absolute value, and alpha is called k. But otherwise, it's almost the same. Now, there is a little bit more here, in the sense that, well, yeah, we get the sequence defined by just repeatedly acting on the sequence defined by the contraction acting on n, giving us the n plus 1. That was the same we just did for the Banach fixed point theorem, right? But what's new here is that it also has an estimate, right, on the error in the nth iterate relative to the fixed point you're looking for. So you see, even if you don't know what this is, you can bound the error, how far you are away from the error in your nth iterate. How do you bound it? You can bound it by the contraction constant to the nth power times the absolute value of the difference between the 0th and the first iterates divided by 1 minus the contraction constant. And I think that if we went back, we probably can, I think we can argue the same estimate for the Banach fixed point theorem that we went through earlier in this lecture. I think we could tack this on to our fixed point theorem as well. See, this tells you how quickly you're converging to the fixed point that you're interested in, which is kind of cool. And then if you look at the proof that is given here, it is verbatim what we just went through, but with norms. All right, same song and dance. Instead of having z, we have x star. Instead of having w, we have x star star. But it is exactly the same argument. All right. So let's move on past that, since we already did that in more generality. Here's the application. Let a function be from a closed interval to the reals be differentiable and bounded between f of a, suppose it changes sign, f of a less than 0, f of b greater than 0, okay? And let's suppose the derivative is bounded between little m and big M. then here's the deal. Given x not a point in AB, the sequence defined iteratively by xn plus 1 is equal to xn minus f of xn divided by m converges to the unique root x star of the equation f of x equals to 0. See, we know there's a unique root because we have presupposed that the derivative has no critical point. See, the derivative is positive. There's no turning point for this function. It crosses 0 because the intermediate value theorem demands it, and it only crosses it once. So there's going to be a unique solution here. That's clear from the calculus of the problem. But anyway, so it converges to the unique root x star of AB of the equation f of x equal to 0. Moreover, here's a estimate. Here's a bound on the error of that iterate. Your error is at most your initial guess divided by little m times 1 minus m over m to the n. This is a upper bound on the error of your iteration. That's pretty cool. And so the proof of this theorem basically amounts to showing that the mapping phi of x is equal to, x minus f of x over m is a contraction on AB. And so, let me talk you through it here. So if we define phi of x to be that, phi prime is this, but remember we've assumed that f prime of x is, bounded, and so that implies that we've got 0 is less than phi prime rather, less than or equal to 1 minus, so the smallest f prime can be is m, so I put that m over m, and that's what I'm going to call k. So that's going to be less than 1, and that gives us, among other things, that phi is non-decreasing, and we can see then that a is less than this, is less than phi of a, is less than phi of x, is less than phi of b, which is equal to this, which is less than b. So we need to prove that for this context, because we need that the contraction mapping is into the closed interval. See, this proves that the image of phi is actually inside the closed interval from a to b, all right? So, great. And then here's the proof that it's a contraction. So the proof that it's a contraction down here, we've got phi of x minus phi of y is x minus y minus that. And so here I'm using something called Carathéodory's theorem, which is just a characterization of differentiable functions in terms of what I call the quotient function. Listen, we can talk more about this some other day. Let me just say this is by Carathéodory's theorem. You could use the mean value theorem here if you don't like that. But by some means or another, nothing too sophisticated here, you get you can factor out the absolute value of x minus y from this and that, and you're left with 1 minus this over that. Now anyway, so this is what we want. This is that it's a contraction. And sorry, I'm trying not to take too much of your guys' time today. I took too much of it the other day. And all right, so we've got, this is our alleged contraction map, and we proved it's a contraction map, and we've assumed all this, right. Now what do we get? So the contraction map theorem applies. That means we get a fixed point. What does that fixed point do? Well, phi star equals to x star equals to phi of x star is equal to x star minus f of x star over m. Well, what does this mean? Well, that means that f of x star must be 0, which is what we were trying to find a solution to. Voila. And yeah. And also, we can look at the error estimate in our, contraction mapping theorem, and when we apply that to the given contraction map, we get the error estimate that was claimed. So this, I would say, is a modified Newton's method, and it is an improvement of Newton's method, Newton's naive method, because it comes not only with a means to iterate, but it also comes with an estimate of the error at each stage in your iteration. You can tell how far you are from the truth. The interesting thing is, you can twist this just a little bit, and you can prove the inverse function theorem. And so that's what I'm doing here. Like if you've got f of a equal to b and y is close to b, can you find x such that f of x is equal to y? So if you try to solve that, try to solve the linearization of that problem, that leads you to this when you solve for x. And then, well, let x naught equal to a is your first guess. And then x1 would be when you feed x naught into this, and then just keep going. So you're basically modifying the idea of Newton's method to just try to find y as a function of x in this sense. And then you can prove that if you have a function that is once differentiable, and you've got f of a is b, and you've got the derivative a is non-zero, then, well, there exists a neighborhood of a and a neighborhood of b, such that if you pick y star in the v, then you can find a sequence in U which converges to a point for which f of x star is equal to y star, like that. And so the way to solve for x such that it produces the y star, right? Given a y star, how do you find an x star that goes to this? Well, you set up this sequence and you iterate, and the limit of that sequence will give you the the x which maps to y. All right, that's kind of, I mean, it's when I first saw this, I was just like, this is just dark magic. I mean, I don't know, it's just, and so here's the proof that, you know, it is in fact a contraction map. It's kind of more of the same, and the details aren't really important to us at the moment. The larger point, though, is this, that the point at the end of all this is really all I wanted to say for today, is that this gives us an iterative method to calculate the inverse function locally. For y and v, we define g of y to be x in u such that f of x equals to y, and that makes f and g inverse functions. So basically, you define the inverse function sequentially as the limit of the sequence of functions that, you know, is so defined. And then the thing is, that means that you're setting up the inverse function in terms of this sequence, this iterative sequence, right? So you can then prove properties about the inverse function. Like you can prove that, you know, if you have a differentiable function, then its inverse is necessarily, you know, certain properties and so forth. But anyway, more of that is in Edwards. I just wanted to kind of give you a flavor for how these things start to be applied. What I want to do Friday is to try to see if we can't come to an understanding together of how the fixed point theorem is used to, say, prove maybe one or some of the major existence and uniqueness theorems in differential equations. You might be like, what? I know. So, I printed something out here. I'm trying to get it on my table. It's covered up. So I will have to give this to you guys as well. So here is, just to give you a preview of where we're going Friday. This is chapter 13 from Nagel-Saff and Snyder, your differential equations book, right? I forget. I think this is edition 5. I don't know what edition you guys have, but it doesn't really much matter. I will send you PDFs of this chapter 13 so you'll have it in all of its poorly scanned warpy nature. But as we'll see in here, you know, you define an integral operator for which the fixed point of it corresponds to solving the differential equation, and then essentially the argument, which is, as you can see, Banach fixed point theorem. And so, like, eventually once we get past this stuff, you define something called Picard iterations, so I should talk about that. Basically, the Picard iteration is just setting up the operator for which the fixed points of that operator are precisely the solutions to the differential equation you're interested in. And since it's since the Picard operator gives you a contraction, you get existence of solutions to your differential equations. And you know, it's actually got the Banach fixed point theorem for operators, which we've already proved. And all the way, yeah, we've already proved. And so maybe it would be good for us to. I mean, I still haven't settled on my target for Friday, but maybe we'll do this one. Like we'll try to prove the existence and uniqueness theorem for differential equations, because by golly, I know you didn't prove it in differential equations, because no one in their right mind would do that. I mean, even in my darkest days, I wouldn't try to prove existence and uniqueness theorem in the differential equations class here, goodness gracious, or anywhere, yowzers. Maybe we should do this one, though. This is the Picard's theorem for systems. This is the existence and uniqueness for systems of differential equations. It's all the same basic idea. Then over here, there's continuation of solutions. I think that's still this Banach fixed point theorem stuff. So I don't know. Anyway, we're going to prove something in appendix, chapter 13 rather, of the Nagel-Staff and Snyder book, which I think essentially, well, I don't know, I wonder in the most recent editions of Nagel-Staff and Snyder if it's even in there. Well, hopefully it is. But anyway, hey, that's where we're going. I seem to have gone 7 minutes over today, so sorry about that. See you guys. Hope you're all feeling better by Friday, so thanks guys.